Now, carboxylic acids are a group that you should know from Year 12, and obviously this is a functional group at the end, so when we're naming it, that's always the number 1, this carbon here. So the chlorine here is on the 3rd carbon, and this would be 3-chloro-butanoic acid. Okay, now just to change this a little bit, if we change that from a Cl to an OH, now this isn't often asked, but it has been asked once, and that is, obviously that looks like an alcohol group, and it will react as one, so if you were to oxidize this with dichromate, that would change to being a ketone group. However, in naming it, we consider it to be a hydroxy group because, oops, that's just hydroxy because the acid takes precedence. Now, carboxylic acids, simple test for them is to turn blue litmus red, and if you were to add a metal such as magnesium or zinc, that would be an acid-metal reaction, and you'd expect to see bubbles of H2. Any kind of carbonates also you'd expect to see bubbles, but in that case it would be bubbles of CO2. So the naming's reasonably straightforward. Okay, now when we consider the physical properties of them, it's all about this COOH and the CO, and this O being bonded to the H means that this has the ability to hydrogen bond with other molecules, and in particular the interesting thing that they do is form these dimers where you've got a OH from another carboxylic acid, and that causes an attraction between them, okay, and they form effectively 2 molecules bonding together. Now that means their ability to hydrogen bond and form dimers means that they've got the highest of all boiling points and melting points of the organic chemicals that we're studying. So that's an easy comparison to make. That also means that they tend to be soluble as they'll hydrogen bond with water, but generally up to 4 carbons, so up to say butanoic acid. After that the non-polar chain takes precedence, and that of course makes it insoluble after 4 carbons. Now these reactions you're expected to know last year, and this is just an acid plus metal, and that's going to make CH3COO, and I'm going to put brackets around that because it's going to be M and G, and there's going to be 2 of them plus H2, so that means we'll have 2 of those, and that's just really the salt plus hydrogen, and this is an acid plus base, so this would just be CH3COO Na, and that's plus H2O, and this would be similar to the top one where we get the CH3COO2 calcium plus H2O plus CO2, so to balance that would put a 2 there as well. So those are the kind of standard ones from last year, and they're not always asked in Year 13. However, this reaction where you have, say, a carboxylic acid and water, and you get this typical dissociation reaction where it forms, the conjugate base. Oops, and that's going to be plus H3O plus, is one that you'd expect to know, okay, as well. So, in other words, this H here is going over here, so it's a proton donor, so that's an acid. The water is acting as a base, it's a proton acceptor. We end up with a conjugate base, because it's, and we also end up with the H3O plus, the reason it's going to be acidic. Okay, and the next reaction that we're going to look at, now this one should be very similar to the previous one that we've seen in alcohols, a substitution reaction. So we can use either any of these reagents really, but again SOCl2 tends to be preferred, but it's going to be this OH group being substituted for a Cl group. Okay, so we just really have to draw out the exact same thing. Now I'm drawing it down here simply because I don't have room, and the Cl is there, and then we just fill in everything else exactly the same. Now this is an acyl chloride or an acid chloride, and there's 4 of them, so butan, and it becomes oil chloride. Okay, so that's one you'd expect to know as well. Now these next reactions are fairly similar, and it's a substitution reaction. The NH3 is coming in to substitute the OH. Again, see how similar this is in many respects to the reactions that we saw with the haloalkanes. This is different though, where we're getting the OH substituted instead of the Cl. Now this is a little bit more complex than that, so if we look at the final product here, we've got an N bonded directly to the C. That's an amide bond, and this itself is called ethane, and then we just add amide. It's an amide, different to an amine because there's that C double bond O there. So this has got this is a secondary amide. You don't need to name these, but that would be methyl ethyl amide. Now there is an in-between step here, so it's necessary to heat this, because if you don't heat this, because this is an acid and because this is a base, it will form something else in between, and that's going to be CH3 COO minus, because, and NH4, I'm just going to get rid of this on this side, NH4 plus. So it forms this salt here because we get an OH going over to the NH3 as an acid-base reaction, but if you heat it, it will then form this amide. And the same is true for this one down below. We'll get the CH3 COO minus and the CH3 NH3 plus, and then if we heat that, that forms that. So if we don't heat it, we just get an acid-base reaction. Okay. Anyway, these two are very similar. It is important to know that it will basically not make the amide. It'll make this salt instead if you do not heat it. And but it is a way to do a substitution reaction of that OH group. And that's that. This next reaction, I cannot emphasize how important it is to know it. It's for making an ester, and it's a completely new type of reaction. It's a condensation reaction. It's when you get two molecules that come together to make a condensed or smaller molecule with the elimination of a small molecule such as water, or in many other cases HCl. Now we've got, it's important to know what the concentrated sulfuric acid is used for. It's used as a dehydrating agent. It removes H2O. In fact, it removes the OH and the H there. And it also acts as a catalyst to speed up the reaction. Now in the actual making of this, it's also important that you can reflux it for a while to try and get maximum yield. So you react all of these three with the concentrated sulfuric acid, the alcohol and the ester, the acid together, and then you would distill off this, which is an ester. This has the lowest boiling point, so it will come across. So knowing that's important. A carbonate is typically added to try and neutralize the concentrated sulfuric acid, and then this is distilled off, as I said. So four things there to know. Now drawing these, I've done the condensed formula, but I've left this. When we draw this, we're just going to, it's important to know that the C double bond O comes from the acid side and the single bond O comes from that. So when we draw them together, it's just a matter of drawing them out exactly the same. Oops, except I've put too many in there. And so that's this structure here from the acid. So if there were more carbons, I just draw more of those in, and then it's just a single bond to the O, and then we just draw, which is, and this single bond O here is this one here, and then we just draw out the rest of the alcohol. Now if that was longer, we'd do it longer. Now it's important to just make sure, to realize that it doesn't really matter which way you do it. If I'd swap this around, I could swap this around and have the alcohol side on that, as long as I have the right number of carbons. Now this is an ester. You name the alcohol side first, which is methyl. The kind of if it was sorry, I must write that methyl. If there were two, it would be ethyl. If there were three, it would be propyl. If there were four, it would be butyl, and so on. And the acid side comes second, which is that side, and that's methyl, and that's ethane because there's two of them, and you just add OH to make it an ester, to show that it's an ester. That's an important reaction for carboxylic acids to know. and also to know the experimental side about the refluxing to improve the yield, increase the rate of reaction, the carbonate that's used to neutralize a concentrated sulfuric acid, the fact that the concentrated sulfuric acid is used as a catalyst as well as a dehydrating agent to remove this H2O, and then finally that the ester itself is distilled off as it forms because it has the lower boiling point. And that's carboxylic acids. Okay, now just a quick summary of the reactions. The typical acid-base reactions with carbonates and metals. The dissociation reaction, which is just showing how it forms a conjugate base on the other side, and the hydronium ions. Substitution with any of these three reagents, and that makes an acid chloride. The substitution with either CH3 and H2 or NH3 heat to make an amide, and then the ester, which is an alcohol plus a carboxylic acid using conch sulfuric. Those are the ones you should know.